No worries. The video is posted to the module, so you can go back and watch it. It's only 5 minutes long. I want to take a moment to welcome Rob Weiland. He is a professor. Let me put you in speaker view. Oh, well, that just makes me there. Okay, let me pin you. Let's see, pin. There we go. So he's a professor here at Cabrillo, and he also is an, I want to say, ocean engineer. You'll see.
I'm an ocean engineer with the U.S. Geological Survey in Santa
Cruz. Right. And so we invited him here so that you guys could hear a little bit more about Rob's educational and career path, because to become an ocean engineer, there's a lot of different paths you can take to find your way into that field. So Rob, go ahead, welcome. And yes, please tell us.
Well, just to give you my educational background, I started off as a manufacturing engineer from Boston University. And I worked for 2 years in factories when I got out of college as an engineer. And I said, gosh, I really love engineering, but I really hate factories, as it turned out. So I had a friend who just happened at a baseball game, Red Sox game, said, hey, I'm going to school for ocean engineering. And upon hearing that, a year later, I was in ocean engineering school at the University of Rhode Island. And I tried to pursue, I ended up getting sort of a geotechnical emphasis in my ocean engineering degree, but I really wanted to study beach processes and work in that area. And I was very fortunate to be able to do that. So my first job I got was with the Naval Postgraduate School in Monterey. And I worked there for 20 years, helping support any kind of research that they do, everything from beach processes to the melting of the polar ice caps. So it's been a good ride. And then I moved up to Santa Cruz with my wife, and the commute to Monterey was killing me. So I took a job at the USGS here in Santa Cruz, and I love working with these folks. They also do a lot of beach processes, but they also do a lot of bottom mapping of the ocean. And we do a lot of beach studies and seismic studies, looking for faults and possibly looking for tsunami hazards on the West Coast here in particular. So that's kind of a brief me.
That's great. And you also now teach statics? No, engineering 35. What is that? Engineering 35.
It is statics. You got it right.
It's statics. Okay. So these our students today in class may see you because engineering 35 is like something you would take your next semester possibly, right?
Yeah, usually a sophomore level class.
Yeah.
Joanne and I have been co-teaching it currently, and then hopefully eventually I'll get back to teaching it full time, but we'll see how that goes.
Cool.
So yeah. I think it's one of the most useful classes for anybody who's can do anything mechanically inclined, unless you're going to do completely electrical engineering. But even then, sometimes you get involved. But it's a pretty basic, important class.
And can you talk about some of your projects, perhaps, that you've worked on?
Yeah, if you want to share, let me share my screen.
Yeah, go for it. I don't know if I have to remove the pin. You can share your screen.
Okay, there it goes. And right here. All right. So this is a project I was involved in. This is in southern Monterey Bay. And we were trying to measure what the wave and currents do in the surf zone. And so we created a large instrumented pole here with all sorts of instruments to measure current and salinity and the amount of bubbles in the water. And this is a whole group of us trying to put that instrumented pole into the water. You can see here on the left, there's a pump that basically jets water and allows us to put things in. I did a lot of this kind of work for, I don't know, maybe 15, 20 years of this kind of stuff, working in the surf zone. It's a lot of fun, but it's also kind of a young man's game. At this point, I think I'd stay on the beach. So.
And you say that because the waves are really powerful, or it just needs
Yeah, it's the research itself isn't that, you can do all the engineering part of it, but the actual putting stuff in, you have to be pretty young. It is powerful waves. At one point, I do remember that we were trying to get the stuff out. That's usually when it's more difficult, but you can see the waves are big. At one point, I got so tired I couldn't swim anymore, and I had to ask one of my fellow coworkers to basically take me into shore.
Wow.
I ran
Yeah.
out of energy. Um, So inherently, all of the work I kind of do has some danger to it. So safety is always at the top of my mind.
And as an ocean engineer, then do you find that you spend a lot of your time out in the field?
I spend, when I worked for the Navy, was probably about a month and a half a year. And I worked with the USGS, which is a little more of an operational unit and a job. I probably spend about 2.5 months of the year out in the field. So I spend a lot of time in the office, in the machine shop. But yeah, a good chunk of it's out in the field.
And so in the machine shop, you would be building this device that you guys are trying to set up now,
Yeah,
right?
pretty much everything that I design, I get to build too. So yeah, that's it. I spend a fair amount of time. I wouldn't say a lot, probably a month, a year in the machine shop.
That's cool for our students who want to work with their hands too. So
Yeah, I have a unique job that allows me to really do a little bit of everything. Most engineers, you kind of get pigeonholed into a particular aspect. You might be somebody who does CAD and they would do CAD all day long. I'm kind of unusual in the sense that I get to play with the computer aided design, then go build it, then go test it, then go deploy it, and then move on to the next thing. So I love my job in that regard. It keeps me entertained.
it looks like you have more projects to share with us.
Oh, I sure do. This is the same sort of thing. Let me see if I can zoom it in a little bit. Oops, no. Uh, this is near shore stuff. This vehicle that you can see going into the water allows us to pull what here was behind it was a sled again, full of instrumentation. And this allowed us to move our instrumentation to different locations every day. And so I basically helped design all of the stuff that went on that sled. There was a big armored cable that came back to the shore with a fiber optic in it. And so we were able to get 256 data, basically 256 instruments on that sled to make all the measurements we wanted to. And this thing here, the vehicle, has a little Volkswagen engine at the top that runs hydraulics that drive these wheels down below. And so it can drive out into the water and help you put things in the surf zone where normally a boat couldn't operate. So that was kind of a unique vehicle. It's called the Crab. That's in North Carolina on the Outer Banks at the U.S. Army Corps Research Center in Duck.
Would that still be in the water today, or is that something you put in and then took out?
So that sled, what we would do is they would pull it out with that crab. And then throughout the day, usually 10, 12-hour shift, we would pull it in increments. We'd have a big forklift on the beach that we'd pull it in about 10 or 20 meters every so often. Partly just because if we left it be, the sand will bury something really quick. I have lost a lot of instrumentation to moving sand that buried my equipment and I couldn't get it back. So, in fact, that was the instrument I was telling you about when I almost drowned was because we were trying to get an instrument back that we were having a really difficult time retrieving.
Oh, wow.
We also do,
and
this is with, question?
Oh, I was just going to say, if anybody has a question, feel free to put it in the chat and I'm happy to read it, or you can unmute yourself and ask as well. So go ahead, Rob.
Yeah, I can blabber for a long time, so please interrupt me. This is a jet ski that we put a bunch of equipment on. You can see just to the right of the jet ski driver, there's basically a monitor. So we make a waterproof monitor to go into the jet ski. There's a computer on board on the back, and there's some batteries, and then there's some transducers and a GPS. And this allows us to do bathymetric surveys in the surf zone here, right where the waves are breaking. Normally boats do bathymetric surveys, but they can't get in there without risking the boat and the people on the boat. It becomes quite dangerous. And we've tried going out at low tide, walking out as far as you can go with a person. And there's always an area in the middle that you can't survey. And so, the ocean engineers, we build this kind of stuff. Again, this is more of a young operator doing this. It's somebody who's a little more agile. It's actually a rather dangerous job. And so that's something, again, as an engineer, I got to build up. Here we are doing drone surveys. A lot of on the beach part, the actual part that's exposed, we can now do with drones by using photography, basically three-dimensional photography. It's called structure for motion. And you just take a whole bunch of still pictures with these targets, which you can see this yellow, black, and white. It's basically a target and a launching pad, but we survey in all those locations accurately. And then as we move along and take a bunch of pictures, knowing a couple of spots, we can therefore project all of the topography of the entire beach. And so here in northern Monterey Bay, we've been surveying the beach about twice a year, every year for the last couple of years, and we can get how the beach changes with time and where the sand is going or not going or disappearing. So we also learned to fly drones in the USGS and how to operate them safely. This is a vessel that the USGS owns. I have spent a lot of time on that vessel as far out as 20 miles to sea. We do all sorts of operations on that. That's just what we operate. We've got 2 captains to keep things going and running on this. And we probably have, I don't know, maybe close to $1 million worth of equipment on board there to do all the kinds of things we need to do.
There's a question for you, Rob. It says, did you experience any big issues while traveling from school to school?
No, I did not. I had, as I said, there were 2 years between my undergraduate and my graduate degree. So there was a fair amount of time in between the two. And graduate school is very different from undergraduate. You don't spend as much time in class. You spend a lot more time working on projects. So I found graduate school rather enjoyable.
And if the students here want to go into this degree, what would you recommend that they do?
Well, it is a small field. I will say that it actually is highly competitive. I did not know that. I probably got in at the early start of things, but it's fairly competitive. A graduate degree is almost imperative. They do offer some undergraduate ocean engineering degrees, but a graduate degree is most helpful. Depending on what you want to do, I would say either electrical engineering or mechanical engineering are probably the 2 best ways to get into this field at an undergraduate level. There is a lot of computer work to be done in ocean engineering. It's a lot of electronics, a lot of software, a lot of hardware, and the mechanical will just be well suited because everything ends up being deployed at sea and there's a lot of forces to take into account and materials.
We have another question. I think they're going to unmute themselves. Go ahead, Crystal.
Griffin is talking.
Can you repeat your question, Crystal?
Oh, I don't think he was finished talking.
Oh, sorry.
Okay. Yeah, I besides like getting a job in ocean engineering, like I've heard about engineers that can make like the research, like they designed the actual research measurement instruments and stuff. Like how can a student, like someone who doesn't have a degree yet, like get involved like with internships or like to get in projects where they can get experience while they're not entirely sure what specific engineering specialty they want to go into, if that
Yeah.
makes sense.
Uh,
Because you
how
were
to dip
showing
your toe
young
in the
people
water.
going in the ocean. I imagine that not everyone had master's degrees.
You know, I would just literally on a cold thing, just send out and make as many phone calls. Emails are kind of cold, but if you can actually find somebody who is doing that and call them and say, hey, have you got any, you know, internships or even just positions to work in this field, and be willing, and I say this bluntly, be willing to work for either low wage or no wage. For instance, we do hire people at the USGS. We have a student hire coming on. A lot of people like to call it an internship. I really hesitate that, because what we do is we hire somebody to fill in all the gaps that the higher level staff doesn't want to do, and literally everything from sweeping the machine shop clean to spending all day bolting things or sorting bolts. Ultimately, we end up giving them opportunities to do other things, but they get to expose to a lot of stuff. In fact, one of our current staff members in the area that I work in started off as one of those employees doing that kind of job. And so it all depends on what you're willing, but you know, there's a lot of sacrifice that comes in the beginning. There's always, and it certainly was in my mind that I was get to jump in and do all the exciting stuff right away, and it just doesn't work that way. Nobody's going to trust you with $1 million worth of equipment because you have a degree. They want to see what you can do first.
Are there certain classes or experiences that might better prepare students for a job in this field?
Again, when I think about ocean engineering, it's actually a pretty broad field. So you can sort of divide it up into different areas. There's sort of people who do acoustics, people who do the instrument development, which is what I think Crystal was talking about, and I've done a fair amount of that, and some of the mechanical stuff. And you could even be involved in the chemical stuff, or even the software, just plain writing software for a lot of this stuff. I have a friend who owns a company that does nothing but software for oceanographic, equipment. So it's just software. That's all he does. Depending on what area you want to be involved in, so if you wanted to be involved, like I said, I think the electrical and the software end of things is where most of the field is going now. I would tend to stay away from the mechanical, which is sort of how I approached it. But the software and electronics are really driving the field into new areas, and that's the area of growth, I would say. So I would get involved in those things. So software classes, electronic classes, even some science classes. I know at Cabrillo, I don't know if the fellow's retiring, but there's a guy who does geology, beach geology here at Cabrillo. Can't remember his name, but he has you actually go out and do some field measurements. So
That's really cool. I wonder, so if you went into software engineering as an example, could you find yourself working in ocean engineering and be able to work in the field? I think most people would think software engineering, I'm going to be behind a desk all day, but maybe there are opportunities for software engineers then.
Absolutely. When I'm sitting on this boat that's in the picture right here, I'm literally sitting at the computer almost for 8 to 10 hours operating the equipment. And a lot of that is preparing that software to be ready to and hooked up to all the instrumentation before we go to make sure it all works right. And then I operate it, for 8 to 10 hours a day out on that little boat. So yeah, there's definitely room for people who are software proficient in ocean engineering for sure. And to be honest with you, I work in what they call the marine facility, and there's 8 of us who are really the technical people, not the scientists, but the technical people. And there's only 2 of us that have ocean engineering degrees. Some people are physical scientists. Some people are geophysicists. So there's a broad range.
Very cool. Do you have a favorite project that you've worked on?
Favorite project. I think you asked me this before, and I always have a difficult time. I've worked on a lot of neat projects. Some of my favorite projects have just been because I got to travel to really neat places. I have traveled to, Alaska and Holland, and those were a lot of fun. But probably the neatest project that I think I've worked on was, and I didn't get to go to the Antarctic, but it was finding a way to measure how much ice was melting on the polar ice cap of Antarctica. So how fast those glaciers were melting, and we had to develop a set of instruments to make that kind of measurements. And that was really challenging.
That is so cool. Now, who gives you these projects? Where do they come from? Like, how is it determined that this is now the project to work on?
That's a really important question, not just a good one, but an important one. So typically, because I work as an engineer, not as a scientist, and I work for scientists. Scientists come up with these ideas about what they want to do, and so they have to apply for funding more than likely, usually from like something like the National Science Foundation, or in some cases private firms, but usually some governmental agency will fund the research that we're doing, and then that research will drive, based on the questions that they're trying to answer, that will drive the engineering side of things. What kinds of things do we need to do to make those measurements that the scientists want to do their research on? So I hope that answers the question.
Yeah, so I guess what I'm hearing is that the USGS sort of facilitates what research wants to be done on its vessels. Is that true? Is that what you mean?
We the USGS in some senses has its own funding, but we also get outside funding. We usually try and collaborate with other research institutions. I will say this, that on occasion when, as an engineer, I will see, as you get exposed, you see all of these things that they're doing, and you talk to the scientists, and you start to see that there are always unanswered questions because it technically can't be answered yet. And as an engineer, sometimes I proposed ideas that might allow them to make this measurement, and then they actually then propose saying, hey, Rob can build this thing. We can now make this measurement. Let's see if we can get the funding to actually go and do all of this. So it's a collaborative effort between the scientists and the engineers, but typically it's the scientists that drive what you're working on, but not always.
That's cool. I think there's another question. Crystal, do you have one?
Can you share more about your experience working for the Navy? Did you say that you worked for the Navy?
Yes. I worked for the Naval Postgraduate School in Monterey, which is different than really, that it is part of the Navy, but it's the Navy's university where they give out master's and doctorate degrees. Unlike the Naval Academy, which just gives out bachelor degrees. We only gave out master's and basically graduate degrees. And that was actually a great place to work. Unusual mix of academics, science, and also military. Yeah, and sometimes it was frustrating because each of those three different entities sees things entirely differently. But it was a lot of fun, and then it was a good place to work. I don't know if I answered your question or not.
Did they, because you went to a school that was funded by the military, did you have a limitation about what your major would be?
Oh, that was where I worked. It was not, it didn't limit my degree because I didn't get my degree there. I worked there. It was limiting for the officers that went to that school. They were basically had to decide within a very narrow field what it was that they were going to study, because the Navy was paying for them to be there, and they wanted to basically educate their officers in a particular way so that they were useful to the military cause.
Yeah, I've seen a lot of like civil engineer. I want to go in like civil environmental, and I've seen a bit of people that work for government agencies too.
Yeah,
that's why I was curious.
So actually, Crystal, I have kind of a narrow view sometimes, but having a civil and environmental engineering type degree is also good for working in the ocean. Both of those things also play into the understanding of what field you're working in, which is in this case the ocean. So.
Right on.
Are there other questions for Rob?
Yes, yes. So my name is Luis, and I have a little bit of I watch documentaries about sonic testing and tectonic plate measurements. Do you happen to have any experience with that? I saw videos of like the UK, how it had a similar terrains with France and places like that. Do you have any experience with that?
Absolutely, I do a lot of that. In fact, this picture that I just popped up is me up in Alaska, and that green spaghetti you see stacked on the deck is seismic hydrophones for measuring the reflections that we put into the ocean. And on the left, the thing I'm almost standing on there, that thing there, and then behind me, there's something that looks a little bit like a broom. That's actually called a sparker, and that makes a big loud bubble noise in the water, sends shock waves down through the water, through the stratigraphy, basically the sediment of the bottom of the ocean. And then the green hydrophones there measure the reflections, and it lets us look at the layering of the sediment underneath the surface of the bed. And by looking at that, they can measure where faults are. And so that's what we were doing, is we were looking for seismic faults, movement of seismic faults, and whether there was any potential hazards in the near future. In particular, we like to look for tsunami hazards, because when an earthquake happens, large tsunamis will be released and be quite dangerous to the people who live in the coastal zone. But yeah, I've done a lot of seismic work in the last 11 years, probably some every year, at least maybe up to a month and a half.
That's amazing. Yeah, I found that so amazing. I was just watching a documentary about that, and I I fell in love with it. Just the history and the how they implement their work, and I just thought it was amazing.
Yeah, the some of the current issues with seismic work is there's a lot of environmental concerns, for biologically environmental concerns, that the sound sources, i.e. the noisemakers that make the big bang, are detrimental to things that live in the ocean. And so we're in the process of finding a way to measure the amount of noise that we put into the ocean, physically measuring it, not just calculating, but taking all of our different sound sources, as what we call them, sound sources, into the water, and then measuring how much energy there is at different distances from the sound source, and also at different depths, because a lot of that will also change with the density of the water. There's something called sound channels, where sound will bounce off of different densities of water. So there's a lot of things to take into account, but we're trying to basically quantify it so that we can say, we can do this safely in certain situations and not safely in other situations, rather than just guessing at it, which is sort of what was done in the old days. It's like, oh, that's fine, which isn't the case.
Wow, yeah, that's amazing. And I had this other question. So you mentioned about drilling in Antarctica, but you weren't able to go. Uh, did you happen to have any research on yourself of figuring out uh maybe, oh, I just want to listen to it, or I want to figure out what's happening?
I'm not sure I totally understand the question. When I say I didn't get to go, there were two other people from my group that went. So, I have direct access to the people who went, and I can query
Oh,
them.
okay.
And they come back and look at the data. And in some cases, particularly when I was working for the Navy, I spent a lot of time also analyzing data. So again, here comes that software component. I don't analyze data in my current job. I'm almost strictly building and operating, whereas in my other job, it was also analyzing. So just a bit of a difference, but yeah, usually you have a pretty good thumb on whatever's happening when you're working with a scientist. And the scientists are always more than happy to share results with you. Ultimately, that's their goal, is to share their results with the world. But the scientists will talk to you and give you what's happening, blow by blow, so to speak.
Are there other questions for Rob?
I have a question.
Go for it.
Hi, Rob. My name's Cody, and I would imagine, I guess it's not so much a question as a statement, but maybe it leads to an answer. I would imagine that back and forth between you and the scientist would lead to helping you develop your instrumentation better.
Absolutely. And like I said, it's definitely a collaborative process between the two of us. So like I said, they usually come with a, we would like to do this, but we don't know how kind of question. And then we go back and forth. Part of this is learning how the engineering process works. Most scientists don't quite understand that. And the idea that things always have trade-offs, that when you build something light, it becomes not so strong. They always want light, strong, fast, quick, powerful. They want all the attributes together that can't exist together. And so you have to come up with a set of constraints and say, well, what is it you're really trying to achieve? And let's make sure that we do that rather than asking for everything. So if we can kind of narrow down the specifications, and that's super important, those conversations going back and forth. And, I don't know how many times we've had those conversations and then halfway through the specifications change. And as an engineer, that's incredibly frustrating because you may have built a design based on a specific specification, and then to have it change, it just means that you have to almost throw what you've designed out the window and start again.
Gosh, that's a perfect segue into what we're going to talk about today, which is the engineering design process. Amazing. We've kept Rob for a while. Is there any other questions that anyone has before we let him go?
I just I love to show this picture. This got a lot of excitement last time. That blue bag and that green bag is my sleeping spot on one of my research cruises. So if you think it's all glory and fun, it isn't. That's where I slept every night for 2 weeks. And it isn't always smooth sailing. I always show pictures of nice calm waters, but it gets rough. And if you get seasick, it's not the best job in that regard.
It looks too short for you. Like, I don't know if it's distortion, but it just looks too short. Like,
it goes back about 2 or 3 feet to the right.
Okay.
It sticks in, but yeah, that's the only private spot you get on the whole boat is that little area. So.
And how long might you be on this boat on a mission, like on a research mission?
Typically my work, when it's offshore and we're on a boat, it'll usually be from a week to 3 weeks long.
Wow. Okay.
And it all usually means little or no communication. And I mean nothing, like no cell phone, no email, nothing, which at first sounds really debilitating. But to be honest with you, after about 3 or 4 days, you just love it because suddenly all of the problems of the world have just gone away for 2 weeks, and you only have to worry about one thing and one thing only, and that's doing your job.
Amazing. Well, thank you so much for joining us. If you want to ask questions of Rob, he's a professor. His email address is rowyland@cabrillo.edu. I'm guessing.
That's
Is that
correct.
right? Okay. So very easy to reach him. And I know that many of you will see him in next semester or the semester after in statics. So thank you very much for being with us.
Thank you.
All right. I hope you guys enjoyed that. It was really nice of Rob to come and join us and talk about the work that he does. And especially after you all, were working on your obscure engineering last week to get to meet somebody who works in one of those fields. I think it's cool. And I want to follow that up with some more information regarding the internships. So at the beginning of class, I showed that video of Daniel DeLeon and the work he did. And he did this as a student through what's called the MBARI internship or MBARI fellowship? Internship, MBARI summer internship program. And I have put in the module a link to that, and you can see the projects that other students have worked on. You can also find that they have application information every year and the kind of work they do. So applications for the 2021 MBARI internship are due February 22nd. So there's still time to apply if this is something you're interested in, and it could certainly get you into the ocean engineering field to get started in that way. But let me just be honest that, you know, it might be something that you may have a better skill set for if you're a junior or a senior in college, but there's no reason not to start looking into it now. So that's given you a little bit of an introduction to ocean engineering. Also, some of the different kinds of work that people do in the ocean between Daniel and Rob. And hopefully you guys viewed the videos from Patrick and Megan prior to coming to class as well. So you have a little bit of aerospace engineering and you know a little bit more about what they do on the job, which is, again, you know, you explored it last week saying, what is this field? And then we got to hear from students pursuing these, or Patrick now in the field working to tell you what he does, and Megan furthering her career or her education on her career path to kind of get a sense of where to go. So hopefully you have a nice broad picture now of those fields. Are there any questions about that? Okay. So what we're going to do, and if you have questions, please feel free to ask me. But what we're going to do now is we're going to take a break. It's 12 o'clock, and we'll take a break till 12:10. I will come back and talk more about the engineering design process, which Rob alluded to when he answered Cody's question. And I'll give you the details of that, and then we will work on your activity for the rest of the class. So for the activity, I asked you to have non-water soluble clay, a bucket of water, and a whole bunch of pennies or coins, something that you could use as weights. Please note that if you got a clay that is polymer based that needs to be baked, it doesn't work. It can't be a clay that needs to be baked. And I didn't understand that before this week when I ran into this issue with another student, that there was that distinction that was made. And so I apologize if that's what you got. If you did, don't open it. You can return it. And then we'll just have to make sure you're in a room with, breakout room with folks who have clay that will work in this instance. So if you don't have clay, before you go on break, if you wouldn't mind posting to me in the chat that you're a student without clay to work with, then I can make sure I pair you with students who have clay. Any questions?
Yes. So would air dry clay be included in that label of non-soluble, or?
Air dry, no, it's the one that has to be baked to hold its shape. And unless it's baked, it just falls apart kind of thing. Okay. Oh, Carlos, I enjoy your humor.
I have a question, Preeti. I was only able to get 2 pounds of the clay. How do I determine the exact amount?
Okay, well, this is what I would do if you have a larger volume than what you need. And I'm so sad that you have 2 pounds of clay. Maybe I can get Cabrillo to buy it off of you for future projects. I'll talk to Joanne about that. But okay, so 2 pounds of clay is 32 ounces. So I would try and cut it into an eighth. If you have 1 pound of clay, I would cut it into a fourth. That's how I would do it.
Okay.
How about if you have 2.5 pounds?
Cut it into a 10. And the way I would do that is cut it in half first. So now you have 1.25 pounds, right? And then try to cut it into fifths or something like that. And if you have a kitchen scale, that's another way of getting to the 4 ounces, is you could just put some clay on a scale that gets you to 4 ounces. You know what I'm talking about?
How important is it that we have exactly 10 ounces is really the question I'm trying to
ask. Oh, it was 4 ounces that you needed.
Oh, okay, gotcha, yeah.
And
we have exactly 4 ounces.
Okay, so how important is that? Not that important, but your results won't be as comparable with other folks. So let's say you wound up using a pound of clay and then you tell me that I held 10 pounds of weight. Yes, because you have more clay, you may be able to hold more weight. Does that make sense?
Sure. I haven't yet looked at the experiment, so I'm not quite sure exactly the
Well,
results.
I haven't introduced the experiment,
No,
but
mean,
that's what I'm saying.
Yes, I'll get it pretty close, but I just want to make sure if I get it pretty close, I'll be within reason.
Yeah, if you get it pretty close, it'll be fine. You know, anywhere around a half. So who said 2.5? 2.5, get it down to
Yes.
2.5 pounds, but that doesn't get us to a nice 0.5 ounce number. Yeah, try and cut it. Get a really sharp knife and just try and cut off a slab if you can.
Okay, perfect.
Okay,
Perfect.
and then, okay, let's see. No, I wanted you to have 4 ounces, not a half an ounce. 4 ounces. Okay, so that's that's a quarter pound. 4 ounces is a quarter pound. Okay. All right. Let's take a break, walk away from our computers. It's 12:03, so we'll come back at 12:15. So I'm going to share my screen. Let's see. Okay, so let's talk about what is engineering design. And Rob already gave you a little bit of a preview of this. But basically what it is a very, I don't know how to say this. It's a defined or structured problem-solving approach. Oh, it says it on the slide. Great. It's a structured problem-solving approach. And engineering design is all about solving problems. So this is the steps we would take to solve a specific problem. So, for example, to walk through this and talk about each one of these steps as to what it means. So the first one is to identify the needs and constraints. So this is, I'm going to use Rob's example. He said he was working with scientists and they said what they needed. And so then he started building something based on what they needed. And then halfway through, they changed what they needed. So to make this process really work smoothly, we need to know what our customer wants. And very specifically, what does our customer want? And what are our constraints? And the constraints might be time, money, how much they're willing to spend. There could be legal constraints, what's allowed, what isn't allowed, material constraints. And then what the need is is, okay, I have this problem, that's the need, and this is what my desired characteristics of the solution are. So they may say, I want it, like he said, I want it to be light, fast, strong, all of those things. But sometimes in saying, well, we can't make something that meets all of those. We can make something that meets 3 of these, right? But you have the customer say, I have this problem. So you really define the problem. And then you say, what would you like from the solution? I'd like it to be strong. I'd like it to be fast. I'd like it to be light. I'd like it to be cheap. And then you say, okay, we'll try and meet all of those things that you would like as best as we can. And you may not get all of them. And then you say, and what are your constraints? And then you say, oh, I have to work within these. So constraints, which I just already mentioned what some possible examples are. So that's the first step, is getting all of that really nailed down. And it could take a long time. It could take many meetings with a customer or surveys, lots of different ways to get the information you need. Then once you've done that, you research the problem. So you do that to better understand it. Okay. You also are looking back at what solutions may have been done in the past. There's no reason to reinvent the wheel. So if there are various little solutions that may be able to be brought together as a possible solution to this particular problem, you research it all. You understand the background for the problem from start to where you are today. So that's step number 2. And then step number 3 is creatively generating as many possible solutions as you can. This is called the brainstorming process. And in this process, no possible idea is bad. You never want to, you usually are working on a team, and, in our breakout rooms today, you'll be on a team. And you want to let everybody on that team speak freely and say, well, I think this might work, or this might work. And they may be the most far-fetched ideas you've ever heard, but you let them all come in, you note them down. Some people put a whole bunch of sticky notes up and say, here's one idea, because at the end of the day, what we have found over experience and time is that the best solution that comes out of this process may actually incorporate various pieces of those ideas. So we want to make sure that we get all the ideas down that we possibly can in step number 3. Then we move to step number 4, where we select one of these solutions. And when we do this, we go back to step number 1 and say, okay, which of these solutions will best satisfy the need within the constraints identified and meet the most of those desirable characteristics of the solution. And then we move forward with that, but we haven't thrown anything away. We're just going to test that solution. And that's where you move to step 5 and you say, okay, let's see if this would work. Is this feasible? Let's build this. If it's a product, then we build a prototype, which is a sample of it. It may be built not with its final materials, but with some cheap material, like you could build something with paper, and that's a prototype, but the final material might be steel. But you want to see how it works just, on a small scale before you go and spend millions of dollars to build a large boat. So we build a prototype, and then we test it. And we test it under the constraints that it's going to perform, and we evaluate it. And this is the part of the process where we might find that this solution doesn't work at all, or it has some problems we need to address. And we go back to step number 3 and we say, okay, I found this problem. Is there anything here that could help me address that? And we do what's called iteration. We go back and forth between step 3 and step 6 of what you see here, constantly improving our prototype until it is completely passes all the testing we have, and we can move on to implementing that. So number 7 is redesign as needed, and that means moving back through 3 through 6 to get the best solution possible. And number 8 is then implementing that solution. So those are the steps of the engineering design process. So now what I'd like to do is propose to you something that has been designed, and I want you to consider how that design has evolved over time. As an example, now let me just see, we have everybody back. Let's see, how do I get to that? 26, okay. So I've put you in breakout rooms, and those will be the same breakout rooms for the project that comes later. And what we're gonna do now is you're gonna go into your breakout rooms and you're going to discuss straws. And you're gonna come up with 5 to 7 reasons why straws exist and how they came to be what they are. I'm not asking you to do background research. Of course you can, but I'm only going to give you a few minutes, so don't spend time on that. Just think about it. Think about the evolution of the straw and what needs may have arose during time that has led to the design today. Okay? All right. So write that down. It's just a straw, a simple straw. And I'm going to go to the breakout rooms, and I'm going to give you 8 minutes in those breakout rooms to, actually, I'm going to make it 7 minutes in the breakout rooms to discuss straws, and then you'll come back. And if you haven't been assigned a breakout room, then please let me know.
Could you remind me what the straws meant?
It's just discuss the design evolution of straws over time, where it may have started and why it is the way it is today. So what would have led to some, so I can go in your breakout rooms and talk about it, and then we'll come back and talk about it more.
Okay, like like drinking straws.
Yeah, drinking straws,
Okay.
exactly.
I
Yeah,
thought
yeah,
you
yeah.
meant like picking rolls, like taking out straws. Okay.
No, I meant drinking straws. Thank you for clarifying. All right. Okay. I'm gonna pause. So tell me, did anyone or what? Tell me, report out from your groups. What did we come up with on when it comes to drinking straws? Anyone want to volunteer to go first? Maybe.
I could go.
Thank you.
Go.
Okay, go ahead.
Okay, so the first one we came up with was physical disabilities. Maybe someone isn't able to raise their hands, but at a level where they could drink.
Maybe paralyzed people.
Yes.
Sure. Okay, so here you've got a need. So what they did was they identified a need, which is I can't drink because I can't use my hands. So how can I solve that need? And then the solution was come up with a straw so that you can stick it in there and bend down without using your hands and drink, right? Okay, so that's great. Anybody else come up with anything?
Fast food.
What about it?
Well, back in the advent of fast food, when there was people roller skating up to the side of your car and you were driving away with your liquid, you can't drive with a cup in front of your face. You have to be able to drink and drive at the same time.
Roller skate.
Or drink and roller skate. That image is vivid in my mind, actually. Okay, so food on the go. Straw made food on the go possible. And actually think about children. Convey that to the back in the time of our, drive up diners versus recently in the last 10 years. What is the use of the straw been?
Marketing.
Well,
they have some straws that are like twisty straws, and I was reading online that they did that to market to young children. Okay,
so the twisty straws are to get kids to use it. So, but that that's a little bit, that's more on the artsy design side of things. Let's talk about functionality. So we were talking about food on the go. Parents needed to give their kids drinks on the go that wouldn't spill, right? So we came up with these juice boxes that have the straws, but they couldn't be the straws that we normally use, the long straight ones. They had to be redesigned to be the size of the juice box and perhaps bend. And there's something else that was put on a straw. Can anyone picture what that is?
The little point to poke through the carton.
So then we got somebody producing these juice boxes saying, well, the straight straw isn't going to go in. So now they had to redesign it and put a point on, right? So they could push that thing through, make it easy for kids to push it through. These are all really good examples. Does anyone else have any other straw invention that was identified for a need?
Oh, actually, Krista found this research about why straws were invented. So it was to avoid the byproduct of fermentation.
It was.
Beer in specific.
Of beer, in specific, yes.
Yes, because there was a residue that was left at the bottom, and this guy said to himself, I don't want to be drinking that. How can I get around this? And he made a straw. The very first straw was wrapping strips of paper around a pencil and gluing those strips together. That was the very first one. So yes, it does come from the alcohol industry. How about other ones? How about other groups? Did you guys come up with any other needs that were identified that the straw met?
For liquids that are higher viscosity, like a smoothie, if you can't pour it.
Yeah, you can't pour it, hard to drink, but you can certainly suck it up, right? So, and those straws might be a little wider than our normal straw. So someone said, ooh, we need a bigger straw, especially for those boba teas with the little balls at the bottom that are huge, right? So now we've got these bigger, wider straws, all right? How about, did anyone think about something recently that's happened with straws due to legal
Yes.
requirements?
Yes. Well, it's not. Well, I guess it kind of is. Environmental redesign from plastic to cardboard.
Paper. So in the 1880s, the very first straw was paper. And then people said, well, these aren't durable. And so in the 60s and 70s, the paper straws were gone and they were changed to plastic. And now environmental regulations say these plastic straws are harming our environment, and we're right back to where we started with our paper straws. So the engineering design process has come full circle in the reverse direction back to point one in this process. Okay. Any other thoughts before we move on? I just hope that you enjoyed that. It was a little fun exercise, and you can do that with anything. Think about Band-Aids. Think about how a Band-Aid came to be today. Okay? Start way back when. What might have been the need? Where might it have started? How did it evolve? What did someone identify later? Like, oh, okay, let's say we have a plain, ordinary Band-Aid. Okay, now someone says, well, I need to carry around this tube of antibiotic, and that's a pain in the butt. And so now they've created Band-Aids that have antibiotics. So you can imagine this is all redesign of the same process. Okay? Good. So you can think about Post-its, fork, toilet paper, bolts, all sorts of any of those things, and come up with a similar sort of, what am I trying to say? Similar sort of process of like identifying what need was addressed by the current design of it. All right, let's go back to my screen. So here is just a little, short history. You can look at it if you want to later. But the key here is that we could use a lot of straws, and so the environmental impact is very critical to mitigating that for sure. Okay, so back to the engineering design process. So engineers use this process to solve problems and, whoops, let me see, this is in the way, or achieve a certain goal. And it can result in a design, a plan of a device, structure, or system. So industrial engineers tend to devise systems of doing things. So their end product may not be something you hold, but how you do something. And they would use this process too. So it's independent of the type of engineer that you become, whether you'll use this process or not. All of them use it. It's independent of the type of problem being solved. It can be applied to any type of problem, and it's independent of the goal being achieved. It can be applied for any type of goal you want to achieve. And some of you may be very familiar with the scientific method. It is similar to the scientific method, but it is not the same. And let me just take a moment to explain that. So this is the scientific method and the picture that you're used to seeing. And as you work through the scientific method, you say, well, okay, I'm going to ask a question. I'm going to do some research. And here's the main thing. You're going to construct a hypothesis. And as you work through it, if your hypothesis is true, great. If your hypothesis is false or partially true, that's okay too in the scientific method. You have proven the null hypothesis, right? And everybody says, that's great. But when it comes to engineering design, that is not okay. If at the end of the engineering design process, your design fails, that is very bad. You have not met the customer need. So we cannot have failure of a product at the end of the engineering design process and say it's okay. The other thing is that the engineering design process is very open-ended, which means there could be more than one solution to a problem. The vast array of straws is more than one solution to getting a drink out of a tiny hole in a container, right? If you look at cars today, let's just talk about that for a moment. The objective of transportation is to move people and goods from one place to another. How many different forms of transportation are there that achieve that goal? Thoughts?
Could you restate the question possibly?
Sure. If we look at just the concept of transportation, the goal of transportation is to move people and goods from one place to another. How many different modes of transportation are there?
A tremendous amount.
A tremendous amount. Can we name some?
Motorcycles, buses, cars, trucks.
So we have wheeled vehicles like passenger vehicles that move individuals and their families or groups. We have trains, we have planes, we have boats. All of those are solutions to the need. Each one of those solutions prioritizes or solves a specific part of that need. So how do we move people and goods across water? Well, we have planes and we have boats. Both of those will do it, right? How do we move people and goods across land? We have personal vehicles, trucks, buses, trains, planes. They all do that, right? Even riverways, we can do boats, different kinds of boats. And those are all good solutions. The point is that depending on how broad your need is, the categories can be just as broad of the solution, and then we can get down to even nail down to cars. I only want to move my family from point A to point B. What can I use to do that? Well, you can use a car. And then someone says, well, I also need to bring my boat with me. So then we go back and we say, okay, well, how do I move a family and a boat together? And we come up with a solution to that. And then you start to see the variety of possible solutions that meet that need. So it doesn't have to be only one solution in the engineering design process. Many solutions can actually meet the need. Okay. So this, I asked you to print this, and this is actually a better representation of the process because it shows it in a circular form here. And what it doesn't show is step 8, which comes out up here, okay? But it does show you all those steps. And the reason I like it to be in a circular form is because you can continue to move through this. It's not linear. You can go back and forth in the engineering design process. So this is a better representation of it. Now, if I were to tell you that the person who figures this out, the need, is different than the person who builds a prototype and is different than the group that comes up with all the possible solutions, what would be needed to make this diagram more complete?
Someone in between the steps who like communicates what the previous step has done.
Yeah, so it's not a person, but let's just say the whole concept of communication. All along the way, to make the engineering design process work, we need communication. It could be communication between two people working through the entire process or 5 groups working through the entire process. When you get into a large company, many times you are only responsible for just one part of this. And without effective communication along the way, the process can break down. And I think I had you watch a video of the walkway collapsing. Did you all get a chance to watch that? Yes?
Yeah.
No?
Yes.
Yeah? Okay. Can anyone tell me why that walkway failed?
Communication.
There was, so in this instance, it's very interesting. There was communication, wasn't there? So what happened is, there was more problems than the communication. So let's just review. Engineers, professionally licensed engineers, designed a walkway. They sent it off to the team for construction. The construction team had never seen such a design before and said, we don't know how to build this, so we're going to change the design to something else. They sent that back to the engineers, and without looking at it, the engineers signed off on it, and the construction people went ahead and built it. It was not, the design was not effective in holding all the weight it was meant to do. With those, it was a different kind of bolt system that they used, and basically the bolts slipped out. They couldn't hold the weight. So lots of failures along the way. One of them was that maybe when they sent back the design, they didn't effectively communicate to the engineers how much the design had changed. The engineers didn't test the design, the new design. So that's right here in this process here. A design came back, they skipped the test part, and they went ahead and approved it. Okay, those engineers lost their licenses and could no longer work as engineers because that was a really egregious error that was made. So communication is super important. Rob also gave an example of where the scientists asked for something and then they changed it halfway through while the engineers were almost done. Communicating all the time is very important. As an engineer, you want to go back and communicate with your customer all the time. Okay. Let's see. So last thing I'm going to ask is, what is the difference between invention and innovation? Any thoughts?
Invention is a new concept, where innovation is a way of changing it to fit a new need.
Exactly. So invention is where you come up with a new idea. And why I want you to consider this is that as engineers today, a lot of the work we do is innovation. It's where we take an idea and we improve upon it. And that in and of itself is very important, because that's what this whole redesign process of the engineering design process gets to. Something's already been designed, and how can I adapt it or change it to meet my needs? A very simple example is the concept of Amazon. What did Amazon do to become Amazon? What concepts did they take?
We went from selling books to selling everything.
Let's start way at the beginning. We had bookstores where you could go and buy books. We had the mail service where you could ship something. And Amazon's roots started in saying, well, why do you have to go to the bookstore to buy a book? I can just ship you a book. So they took what was existing, a warehouse of books, and the shipping service, and put it together. That's innovation. And look where it's led to, a multi-billion-dollar company. And it grew from there, right? So you kind of get the idea. Okay. Oops. Let me see. I think that's all I wanted to say about this. So now we're going to move on to our project. So for our project, oops, how do I get back to you guys? Okay, let me share my screen. What we're going to be doing, and some of you may have already figured this out just based on the list of supplies, is we're going to use the engineering design process to build a boat from clay that can stay afloat with as much cargo as possible in the next hour. And I might have to change the amount of time depending on what we have. So you have your clay, you have some weights, and you have a sink or a bucket of water. And you should be able to answer these questions. So how you use the engineering design process to come up with a design. By the time you're done, you should be able to do this. How many times you change the design of your boat before you get to the final design, and what do you learn as you're changing? And is failure a bad thing at this point when you're doing this? You'll need to take a photo of your final design and a video of your final design sinking, and you'll have to compute the total load carried. And at the module page is a more fleshed out description of this, as well as weights for various coins if you're using coins, so you can calculate the total load that's being carried. And I'll make sure that that's published. I think it is, but I'll go back and check. So one thing I want to talk about is this concept of buoyancy. And buoyancy states that any object in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. And I think on the module page, I have actually put a link to a video you can watch that discusses buoyancy. So you should think about buoyancy as part of your research for step 2 and figure out what that is. The other thing you may want to do is make a ball of your clay and put it in the water and see what happens and try to figure out why. And then that is part of testing your materials, and understanding your materials is a very important part of the engineering design process. And this is also part of the background process, understanding your materials, okay? And then just moving through the steps, okay, and documenting that. Write that down as you move through the steps. You're going to have a design, you're going to test it, you're going to say, how can I make it better? What can I learn from this design? Write that down. Change the design, make it better, test it. That's all part of the engineering design process, and you're using it even if you don't even know you're using it. You're actually working through it. Any questions? And the page has been published, so let's bring it up. Yeah, okay. New share. Let's see here. It's right here, and it is published. So I have this little video on buoyancy. It says what to do. And here are some weights that you can calculate how much your boat is holding. So let's take 45 minutes to work in your groups. And you're going to go back to the same rooms that you were in already. And I think I've done it so that everybody in the room, there might be one person in the room who doesn't have clay. And so that person will be responsible for giving ideas to other people in the room as part of a team. You're working as a team. One person, and this is really a good exercise in communication. How do you communicate your ideas to somebody else who's building something? And so there is a follow-up discussion post. And so if you're in a breakout room and you don't have clay, have one of the people send you a photo and a video of the boat sinking so that you can contribute to that discussion post as well. It's an individual contribution to the discussion post. Any questions? Okay, so the most important thing is to have fun. So have fun and try to learn from the experience. I will be here. Feel free to ask me questions. You can, I think there's a way you can call me from a breakout room, and I will go to breakout rooms that have questions, and I'll just be going between them. Okay, see you all in 45 minutes.
Was anyone successful?
I'll go first.
Okay, who said that? Zane?
Yeah.
Okay, so room 2. So let's do the same things. Let's give room 2 the spotlight. We go to somebody who doesn't have a camera on, click on the 3 dots and say hide non-video participants, and then we stop our video so we only see room 2, which is Jason, Zane, and Aiden.
So what we came up with was kind of a circle with kind of like a rectangular edge. And we thought circle because circles, you know, the area grows exponentially. And so we thought, well, that'll probably work out the best. And so we did that. And then the square edge is that way we're not taking up clay trying to make a round edge. It's just a straight path up. So we tried this. We got 308 grams or about 11 ounces of coins.
Do you know how many coins that was?
Too many to count. I just kept throwing them in until it sank.
Okay, yeah. Yeah, it's a lot of coins to get 308 grams. That's great. Oh, wow. Now, Jason and Aiden, did you also build one? I don't remember how I split up the groups. Oh, you're muted, Jason.
I did, but it was nowhere near what Zane got. I'll tell you that. It was, I'm pretty sure I got like 100 and something grams.
Okay, that's great. That's great. And did you guys use only 4 ounces of clay, or did you use more? Do you know?
No, yeah, I
There's like an estimate. There's like a small little rectangle.
Okay.
This one I did measure. It was like 4 ounces right on the dot.
Awesome. Okay. And what were you showing us, Aiden? What is that small thing?
I ordered the wrong kind of clay, so I just made like a little model boat instead.
Okay.
Do it.
And did you help them out while they were doing their design?
Yeah, I tried to like give some ideas where I could, but you know. Oh yeah, Aiden too. He mentioned the barge idea, kind of like a dredger in the Santa Cruz Marina, how that holds up a lot of weight. So we thought, you know, kind of the flat bottom idea was best.
Flat bottom. Interesting. Okay, great. Did you take a video of it sinking?
I didn't. I'll do it again after class.
Okay.
I'll post that.
All right. So another part of this is also to watch it sink and try to figure out why it sunk the way it did. Okay.
All right.
So that's the next part of this. Did Aiden get a photo from you guys or something so he can post? So make sure you guys send him something so he can also talk about the design on his discussion post.
Okay. I'll send that to him somehow.
Okay, great. Thank you. Thank you guys for sharing. If we would love to see the boats floating. So if the next team to go, the next room to go can show us a floating boat, that'd be awesome. Do I have a volunteer?
I can attempt to do that, but how do I share that?
I don't know. Where are you? Are you near your water?
I took a video already.
Oh, just share your video.
All right, so I'll talk to myself then.
So let me think. Where's your video? Is it on the computer?
It's on my phone, so I'll email to myself.
Okay. While you're doing that, before we get to your video, would your room be willing to share your boats with us? It's Adam, Cody, Ken's, and Jasmine.
So I'm the only one who was able to make a boat because it ends up that I was the only one with clay that was non-soluble. So I
Oh
can
no.
I can show here. I'm sorry. Let me put my video here.
No.
can show
Before
my-
you bring your video, hold on. Oh, there's your boat. Okay, great.
It's loaded with as much coins as I could muster.
Well, you can get some. Go ahead. We didn't hear you. It turned out to be what?
Well, I haven't. I'm just calculating the weight now, but it turned out to be
Oh, I
7
have it.
pennies, 8 nickels, 14 dimes, and 16 quarters. Adam, what did you say?
So I have the weight, and with all the coins, it accumulates to 179.972 grams. So about
Okay.
180 grams in coins. And the thing is that it probably holds more because we went through 3 iterations with our boats. And the third one maxed out because Cody only had a certain amount of coins that we could use, and the maximum was 180 grams. So we could actually take more, we're just not sure how much.
Right. So, Cody, what I would recommend is finding some things lying around your house that you know how much they weigh and adding them in.
I have another question.
Good point, but I'm not quite sure where to start, Preeti.
I'd start in your couch and look for coins. No, I'm just kidding. I have to think, but like 4 ounces of butter. If you have a stick of butter, you could take all your coins out, put the stick of butter in, and then add coins. Do you know what I mean? So there are things in your kitchen that have a weight to them assigned. So I would start with something like that.
Or we could just get like a set volume of water and add that in just so it doesn't go over the
Yeah, you could do the water. I would worry about it sinking faster. If it tips to one side, it'll just suck it up, the water will just go right in. But anyways, what I'd like to hear about from your group is the teamwork aspect of it. So how did you work as a team, given there was one person with clay and 3 people without?
Well,
So at
I
the
had
start-
clay, but once I put it in water, it just soaked it up and turned into like mush.
What kind of clay was it, Ken's?
It said air dry, so I thought it would be okay, but
I think it was
just
the Crayola
soaked
one.
it up. Yeah.
Oh no. Okay.
So I had tried similar designs as him originally, and they just all suck. Like, as soon
We
as I
had
put
a very
them in-
interesting time.
yeah, they just suck.
Well, tell us about your teamwork process. Adam, you were going to say something.
Yeah, so initially it was Cody and Ken's who had the clay that they were going to do. So the way we split it up was Ken's and Cody would make the actual prototypes and test out the weight, while Jasmine and I would come up with ideas. We would write down how many coins got in and what the specifics were. So I opened up a Excel spreadsheet on the side and just wrote down the information. Jasmine was also brainstorming in the background and getting us stuff on the internet. We also got a picture of the engineering process to know where exactly we were in that process. So we tried to like divide it between the physical workload and the more computational and writing stuff down workload.
And Jasmine, what was the most important part of the engineering design process for your group? You're muted, probably. We don't hear you.
I need to get the specific step or
Yeah.
Okay,
The step,
I
yeah.
need to get the picture of it up. Let me.
And Ken's, did it just become a big mess? You just couldn't do anything anymore?
Yeah, I had a lot of clay, and then I was like trying to shove it back together, but it just got all over my hands and all over my desk. So
Okay, sorry about that. That's a bummer.
It's okay.
That was a fun engineering process too, because Ken's even told us that, well, she had to step out to her sink to do all the water testing. but she tried different shapes and different amounts of weight of clay. And she realized that it had to have been the clay because the shapes were too different, the weight was too different. So it wasn't that like the design was wrong. It was the actual clay itself that wasn't sustainable.
Yeah,
Yeah,
so she did a lot of material testing, basically.
Yeah,
and
because I
figured that
have
out.
like a big thing of clay, so I was like, okay, maybe it's just too much clay, but no matter what I did, it just kept sinking.
I see.
To answer your question about the engineering process step, I would say that the most important part was somewhere between improving and asking what went wrong and what we could work off of that.
So
Like
what you're saying is like testing and redesign. So
Yes,
test,
yes.
figure out what went wrong, and design again. Yeah. And you did a lot of that. It sounds like you had 3 versions at least.
We had 3
Yep.
different versions.
Okay, great. Cody, did you want to come back on? Were you able to find some weight or no?
So I've got 4 ounces of butter and I'm stacking quarters now.
That's pretty great.
That's awesome. That is
That's
awesome.
great.
And you know, for anybody else that's run out of coins, that's the idea I would give you is go to your kitchen. And many of the items in your kitchen are weighed for you, like a stick of butter. Can anyone think of something else? I'm racking my brain, but I'm not coming up with other than butter right now. A package of crackers. Go ahead.
Bags of dry beans and dry rice, usually that has weights amount.
Yeah, but it might be too much to add all at once. But yes. And I was just about to say like a small package of crackers. Like if you have, you know, those, like a granola bar on the go, anything really small that you could, that comes with a weight on it could be used. So the first thing you want to do is get your small coins in there because you're adding weight very gradually. Once you've established that a certain mass of coins works, you can pull them out, put something heavier in, and then again gradually add the coins. So that is the scientific way of testing is to add very gradually, but you can always substitute the gradual weight that you've added to date with something heavy that is equivalent, and then continue to gradually add more. All right, before we go on to another group, Cody, do you want to show us what you have?
Yeah, so right now I've got can everybody see what's going on there? I've got the 4 ounces of butter and 16 quarters. And so far it's just on the edge. Every time I add a quarter, it's spilling a little bit more water in there, which is going to skew the results a little bit.
Right, because it's actually taking weight on with your water.
That's right. I'm happy to keep dropping coins for everybody to see.
Yeah, I mean, I think at this point you might want to be just stacking right in the middle, just to make sure that you're not tipping to any side. And then we'll see what happens. And then I guess for this group, you'll need to share your results amongst each other. I'm now revisiting my thoughts, though, on whether we should do individual discussion posts or group discussion posts. So let's see what other people have done, and then I'll weigh in on that. No pun intended.
Oh, there she goes. 9 dimes took her out.
Well, I think you said you had a little water in there too, so you might
It was about
you might include. Okay, nice work. Very nice work. And if you noticed, it went straight down for him. And we'll talk about sinking after we see a few more. Do I have another group willing to volunteer to go? Okay, so I had room 1 and room 2 go. So how about room, oh, thank you, Luis. What room are you? You're in 6, Crystal, Kevin, and Luis. And you're muted, all of you.
Yes, okay. So we had some trial and error. So it came up to the point of what Ken said. I bought air dry clay, and
Okay.
so we still tried it. We still tried it. I was gonna be hopeful that it wasn't going to skew any results, but it did. So all of the different types of ways that we tried to make the clay, it just sank. I have how it said we were supposed to try a ball, and so this is going to be the ball. Wait, let me see. There we go.
Oh yeah.
And so
Okay.
that's how it sank. So I tried a design. It wasn't the best you could make, but it was something. You see, it just sinks. It just
Ah.
sinks. And what I tried was tried a little bit, and yes, it's water soluble. What I originally thought was it was possibly needed to dry because it's obviously air dry. So once I actually opened it up yesterday and left a little bit out, and it actually made more sense if you actually leave it out for a while, and then it just dries, and then you could use it.
So the follow on to this is you could actually make a boat today and let it dry and test it.
Yes.
Okay. I think that's a great idea. Ken's, if you have any of yours left, you might want to do that too. So go ahead, Crystal.
Well, I didn't have my clay, but I watched Kevin, I believe that was our other partner's name, and Lewis make theirs. And the more they used the clay and made a different design, the more it would like crack and become really
Yes.
soft. And so the integrity of that clay like was compromised the more.
So it was also a one-time use then, like you couldn't reshape it.
Yes. And I
Kevin,
actually used the exact, well, yes, the exact 4 ounces. I actually had a scale to measure the exact 4 ounces, but nothing.
okay, well, why don't you try
I actually
having
had-
it dry? Sorry,
I
go
had
ahead.
the same problem. Like as soon as it got wet, it was almost like it was just done for being used. And I feel like
Yes.
I could let it dry out, but it got so malleable that I think it would need a while to dry out.
Do you have any not wet clay, Kens?
No. Are you so happy?
No.
I was desperate to try to make it work. I thought I was doing something wrong until Adam proposed the idea that it was probably water soluble.
You know, you never know what's going to happen with this project, but this semester we have learned that testing our materials is really important. And that's an important lesson for all of engineering design, okay? So it's a good lesson, and I'm sorry that that's the lesson that had to be learned on this, but it's an important one, so it's okay. Kevin, did you build a boat?
Yeah.
Okay, and it worked?
Well, kind of. It sunk down.
Well,
his material also, it was very, I think it was water soluble.
Yes, it was the same
Mhm.
product as mine. So we were both.
Okay. So, thank you for sharing. Look at what other people are doing and see what you can get out of that. Okay.
Yes.
We've seen 2 successful boats. So if you want to try some of your clay and let it dry, consider the shape before as you're creating it, and then check your results. Okay.
Perfect.
Cool. Thank you, guys. So I was saying room 3, 4, 5, and 7. Anyone want to volunteer? Oh, and we have to go fast. So Ruben, room 4. Thank you. Go ahead.
So I came up with this. Well, first it looked like a pizza, like with a thick crust, and I made it like deep in the middle, and I was able to hold a few coins. So then I decided to make it deeper. So it looks like this. This is not the original one. I made it again. This one's not able to hold that many. But the final one was able to hold 27 quarters. That's 153.09 grams, 0.09 grams. Yeah. You want to show yours, Angel?
Yeah, sure. So this is mine. It's kind of like listener, but I did it probably a good time I redesigned it, and so it was too many prototypes I had to use, as well as we Brandon actually gave us some help because he didn't have clay, but he was giving us ideas, and he shows like a picture of one where like of that helped us out, like of like word of kind of how I really designed it. So like Ruben's was a lot more like a circle oval shaped, but mine it's like a flat based type of boat. So and then I haven't tested it yet. The other ones I tested before, I got like up to like 7 quarters, but it kept on sinking because of the edges. They weren't really that high enough. So that's why I had to make the edges more higher up so that the water wouldn't go in so easily.
So I'm gathering, Ruben, you have higher edges in relation to Angel's.
Yeah.
Yeah.
It's like the more deeper I made it, like the more it was able to hold.
Okay, great. That's good. Did you try flattening it, Ruben?
From where? Like
It's kind of a bowl shape right now. Did you try making it super flat on the bottom with your high edges?
Oh no, I did not try that. That's similar like to group ones, right? Yeah.
Yeah, I think so. Theirs was a really wide bowl with flat. Yeah, it was flat and wide. What did you guys find was the key part of the engineering design process for your group?
I think we really focused on the redesign part. Like we just kept improving on the designs.
Okay, cool. And did you use Plastina? Angel, are you using the Plastina from Engineering 25?
Yeah.
Okay. No, that's perfect. Okay.
Oh, okay.
Okay, cool.
Yeah, I got that one too. Yeah, it was from the
Okay.
link.
Okay, cool. Awesome. Do you have anything else you wanted to add?
No.
You're good? All right.
Good.
Thank you for sharing. Okay, how about room 3? Alex, Carlos, and Sam. You muted, Sam.
Oh, okay. Yeah. Me and Alex both made different designs of our boat. Alex's I think was more successful, but let's see if I can show.
Oh, look at that.
And then I haven't put any pennies in it this time since last time it sunk. But yeah, it's kind of like a raft shape, but I think the more I like design it, I think the edges need to be taller, need to be bigger.
So maybe compromising the internal size for higher edges might be okay. Okay. And did you get any pennies? Did you get it to hold any pennies before it sank?
Yeah, I got 14 pennies, I think was the most.
Okay. That's good. That's good. You got something in there. So you're still working on it is what I'm gathering.
Yeah.
Okay. And Alex, Sam said you were super successful. Share with us what you did.
Well, maybe compared to Sam, I was successful, but compared to other groups, maybe not so much.
We're all successful.
Bowl shape type thing. I tried to make like a raft type thing, like a rectangle with like square edges almost, but it was not nearly as successful as this. Not that this was super successful.
How many did you get in there?
Oh, let me go out. One sec.
And after this group, we'll have Cameron, Jose, and Nathan go. Ah, there we are. What's that?
This is my failed raft attempt. As you can see, it's not very it barely floated on its own. And this is what I got in. I think it's around 15 pennies, 5 quarters, and 5 dimes.
Okay, that's great. Now, just to be clear, you have 2 boats there. Are they each 4 ounces of clay, or did you
Yeah.
have that? Okay.
No, I got this this like package of plastilina, and
Yeah.
it's a pound total, and it came with like lines divided into 4 pieces.
Okay. So each boat was a quarter of that. So you did use 4 ounces total. Okay.
Yeah.
Cool. And how did, I think one of your group members didn't have clay, right? Carlos didn't.
No, I didn't.
Yeah, I think you're the one that made the joke. So how did you work with them, Carlos?
I just tried bringing up how they should put edges, I guess, so it doesn't topple over into the water.
Okay.
Yeah, he gave us some ideas of like how to build it and like what shapes might work best.
So Carlos, do I gather you were working on background research while they were sort of working ahead and building?
Yeah, it looked like they had the handle, like everything together, you know?
Okay, cool. So what would you guys do next? What is your next step?
Oh, go ahead, Sam. Sorry.
I was just gonna say just like keep like retrying some different ideas. Maybe go with the bowl shape or like yeah, that's what I'm seeing from other groups that were successful is that strategy. So I'd probably try that. And,
Okay.
Yeah.
Cool. Alex, did you want to add anything?
Yeah, I was basically gonna say I just like keep redefining, or not redefining, but like improving what I already have. I mean, I could try to change it and go to this guy just to see where I could get if I spent a little more time on it and like define the edges more and made it more, because this one I kind of did kind of quickly and there was like holes in the bottom and it's super thick in some spots and super thin in other spots. I just didn't really have a lot of time to really quote unquote perfect it. So maybe just spend more time on that.
Great. So next steps for many of you might be another redesign based on what you've learned from the class today, and then testing that and then submitting that final answer for your discussion board post. Great, thanks guys. Really quickly, room 5, Cameron, Jose, Nathan, do you have something you can share with us?
Yeah, I was the only one in my group who had clay. So this is my boat, the SS Cluster Truck. It's a miracle that it works. It can hold about 25 pennies, maybe 24, hopefully either 24 or 25. It worked last time I tried. But originally it was just a sphere, and we as a group tested how well it would float about 3 to 5 times. Each time it sank. So then we went with the bowl method, and that one could hold about, I think, 10 to 15 pennies. And then Jose recommended trying to make it a little bit longer. So we ended up having this design. It had to go through a complete redesign at one point because I took too much out of the bottom of the boat. So then I just started tearing all over the place and sinking. And then we managed to get this.
Cool. And if you were going to place your pennies in, how would you do that right now?
Delicately while praying.
Okay. The back of your boat seems a little lower than the front. It might be an optical illusion for me. I don't know.
Oh yeah, that was just some. I kind of whipped this up almost in the last couple minutes because that's when I had to do the redesign. And then once it was up, I just kind of like didn't want to touch it because I didn't want it to all fall apart again. Because I have a knack of making things break when I touch them.
Okay, so putting your pennies in really carefully is also critical to this process. You can't just dump them in anywhere, because if you do, like, you can see his boat is kind of tilting to the left right now. Now he's putting some down on the right. So you have to work methodically to distribute the load evenly. Otherwise, if it's not distributed evenly, it will tip, which, you know, we all are very familiar with the process of that. Let's see. Oh, he's even got tweezers. That's pretty impressive. Thank you, Nathan. And then last room, I think, is, I don't know, have we heard from everybody? Alejandro, Reed, and Ulysses, do you want to just show us what you've got really quickly?
Okay, so I'm pretty sure the most successful model we had was this one, the bathtub. It could hold 12 and 5 dimes. It was the best one, I think, out of our group. Yeah.
Cool. What?
I did not
Go ahead, Reed.
have clay. I did not
Okay.
have clay, so I just helped out.
Yeah.
What made the bathtub successful as opposed to previous designs you looked at?
Well, the first one I started with was just like a rectangular box, but it couldn't really hold too many pennies, and it sunk immediately. Well, no, at first it sunk immediately, and it didn't hold any pennies. So I just remodeled it and made it longer and wider, so I had a larger surface area at the bottom, and it held way more pennies than I thought. And then I tried to make a different model where I guess it's wider, wider, but it didn't work out as well. I think it might have been too heavy on the sides. I don't know what happened.
Huh, interesting. I wonder if you could try that again and see if you run into the same problem.
Maybe.
Alejandro, did you want to add? Sorry, go ahead, Ulysses.
Well, I also made a boat. Ulysses's held more than mine, because mine usually so I did like more a rectangular shaped, but for this one it always ended up getting like water creeping in through the sides. Because for this one, what I found out was a lot of it had to do with balancing out the coins, and every so often it would tip over to one side, and then all the water would go in.
Again, coin placement, super important. So I don't think we have any more time because I think class is over. So I just want to wrap up and say great work, everybody. Great work working in teams. Working in teams is a critical part of all future jobs, no matter what field you're in. So it was nice to hear that. I hope that you realize that as a class, you've come together and shared various techniques as if you were all prototyping the same project. And you can now go forward and take what you've learned from each other, from all the other groups, and try to get your best design still. One thing I may offer is I noticed that many of you seem to be working with the clay with your fingers. And having a very even layer of clay could be achieved by rolling it, perhaps, before you bend it up. Something to think about weight distribution of the clay is how can you get a very even layer on the bottom? Something to think about. Okay, so last piece of this, and I think I am going to leave it individual, is for you all to post to the discussion board your experience. It asks you to, I'm in my inbox, it asks you to talk about what you did in your groups, and also to post a photo, and if you can, a link of your video, a link to a video of your boat floating, sinking, but in the process, actually just talking about what had happened. So if you can't create a video, no problem. Just talk about it. Show a photo. If you didn't make one, get a photo from your group and just answer the prompts here. I'm going to leave it individual. Okay, everybody should post individually. In addition to that, there's a follow-up on our speakers and our videos that we listened to and heard from, and so that is also in the discussion. So this is discussion 3A is our clay boats reflection, and discussion 3B is a guest speaker reflection. And just to tell me that something you learned, which was new to you from the videos and the presentation today. And those are the follow-on for today. Any questions?
Well, have a question for the people in my group. If they could private message me their phone number before this meeting closes, because I need a photo.
Okay. Good idea. And if anybody else needs to do that, please feel free to go ahead in the chat and use that as a way to communicate before we depart. The other thing is that the Canvas site has a people option on the left, and you can always click on that people option and send a message through Canvas with one of your group members. Okay, so that's an option too. Next Thursday, I won't see you. It'll be Joanne. She will be talking about engineering education, and she has a couple things for you to print before class. Homework is due Monday. The chapter homework is due Monday. So that's all I have today. Great work. I hope you had fun. Oh, bring your coins the next time I see you, which is in 2 weeks. We'll be using those coins again. So if you don't have any coins, you'll need coins. Go get pennies. And then we'll be doing another project that uses that. Cool. I am leaving. Thank you. Yep. I'm leaving it open so that if you need to communicate in the chat, you can. But otherwise, we're done with class. So.